Hello everybody, and welcome back to another quiz tutorial. In this tutorial, we're going to be covering quiz number 21, which is the classification of materials. So as you guys will see in this section, we already know how to deal with stresses, and we already know how to deal with strains. And what we're going to do now is try and figure out, okay, well, if I know the strains, how can I find the stresses? Or vice versa, if I know the stresses, how can I find the strains? And in order to do that, we have to understand what kind of materials we're dealing with. So quiz number 21, nice simple quiz. It's going to go through a bunch of materials and we're going to try and identify some key properties of them. Now, what I like most about this quiz is it shows you the wide variety of materials that you'll deal with as a civil engineer. There's a lot of structural ones. There's a lot of biomechanic ones, biomedical, I don't know what to say, biomechanical ones. And even though it's not featured in this quiz, one of the big ones too is also fluids. For those of you who are interested in CIVI 330 and all those fun fluid stuff, as you guys will see, fluids have their own properties as well. But in this class, of course, we're kind of sticking more towards the civil materials, which is concrete, steel, etc. So let's jump into the quiz so you guys can see what exactly we're talking about. All right, so this quiz is nice and short, 6 questions. I don't even really need to cover the theory because Dr. Sammer did such a good job of that. If you guys want the theory, just check out his nice little YouTube video, 6 minutes long, and he discusses absolutely everything you need to know for this quiz. So all we're going to do is we're going to look at some pictures, and it's nice, a quiz with pictures is always fun, and we're going to try and classify some of these materials. So the first one, it says the picture above depicts a dent in a pipeline. The pipe is originally cylindrical, but during installation or due to mechanical interference, permanent dents of these can form. So it's asking what kind of response does this material exhibit? Now, the key here is permanent dents. So what happens is we take something like this steel, we load it, it gets deformed, but here's the key. When we unload it, there's still that deformation. Now that's what we consider a non-elastic response. So if we load something and unload it and there's that permanent deformation, that's the non-elastic response, D. Now, if you guys pick D, I believe that the quiz will give you the marks, but here's kind of a little trick. What happens when we're considering the non-elastic response and permanent strains and stuff like that? The only way that those are going to be possible is if we have a non-linear response. Because what happens when we load something and unload it a bunch of times, we get something called a hysteresis loop. And what the energy is that causes these permanent strains is the area between the loading and unloading curve. Now, if we had a linear response, there's no area between the unloading and unloading curve, so there's no energy dissipation. However, since we have these permanent strains, there must be some sort of nonlinear response. So the most correct answer for this would be B as well as D. We have a nonlinear response and a non-elastic response. The non-elastic response is very easy to see because if we look at our material, there's that permanent deformation. So if we go E, which states that it's both B and D, I'm going to just check the answer, and we got it correct. So looking so good so far, it's going to be pretty embarrassing if I don't get one of these correct. So we'll go on to the next one, and we got a piece of wood. And it says, as a structural engineering material, wood fibers, the cause response is dependent on the loading direction. Now, right away, just by looking at this question, whenever you hear about loading direction, that has to do with isotropic, anisotropic, or orthotropic responses, where orthotropic is just kind of a subcategory of anisotropic. So what it basically means is isotropic means it doesn't matter which direction I load this in, it's always going to exhibit the same response. Meanwhile, in anisotropic materials, the loading direction does matter. And if we look at wood, we can definitely tell it's going to be anisotropic. There's a reason why when we're chopping wood, we make sure we go with the grain. If you lay down the log horizontal and try and chop it down like a beaver, you're going to be there for a long time. However, if we have it vertical, we can chop through the fibers nice and easy. So this is what we call an anisotropic response. Now, more specifically, if there's 3 different loading directions, we can call that an orthotropic response, which is a subcategory of that anisotropic response. So if we look at our answers here, we have B, which is isotropic, and C, which is orthotropic. We definitely know it's going to be orthotropic because, again, isotropic means that it's the same in every loading direction. And we know in wood, of course, that's not true. The going parallel with the grain is going to be a lot different if you're going perpendicular with the grain. The other 2 answers, the linear response, well, we don't know the response. And D, viscoelastic, well, again, that's time dependency. We're not talking about time dependency. Again, if we look at the question, it talks directly about the loading direction. So we can narrow it down to B or C, and then we know that since the wood is different based on which direction, we know it's going to be C, which is an orthotropic response. So I'm just going to click check. And we're 2 for 2, so looking pretty good so far. Moving on, and as you guys can see, this is definitely a U of A slide, so I guess that this pipeline is probably right from Dr. Sammer's research, because as you guys may know, that's exactly what he does, is pipeline research. And it says the figure above shows the true engineering stress strain curves of the specimens obtained from different locations in a pipe. For example, specimens from the weld area show that by design, the weld exhibits a higher yield and ultimate strength than the base metal. So here's kind of the key here, is 2 different parts of this material exhibit a different response. Areas of the weld show a different yield strength and ultimate strength as compared to just a regular part of it, or away from the weld. So we call this a non-homogeneous response. So that'd be C right here. Again, orthotropic response, we don't know because, again, these steel tension tests, we're always loading them in the same direction. We don't know. Viscoelastic, that means it has something to do with time. Again, we don't know. So it really comes down to B or C. Homogeneous means that no matter where I take the specimen, it's always the same. However, we know that's not true because, again, areas around the weld exhibit a different response. So therefore, we know it's a non-homogeneous response, or part C, or I guess answer C. So let's go ahead and check that and see what we're looking at. And we got it right again. So 3 for 3 so far. Let's keep up the momentum. Moving on. This one I like a lot because this is something called pre-stress concrete. And even if you guys graduate with your BSc, unfortunately, you guys will not get into the topic of pre-stress concrete. The reason why is it's not only sophisticated, but it's actually very dangerous. A lot of structural engineers will choose not to deal with this pre-stress concrete because we pull those steel rebar and it's so tight that sometimes they explode. And it's very scary when they explode. And oftentimes, if you're the worker there tightening these or pre-tensioning them, you're going to die. So a lot of engineers choose not to deal with pre-stressed concrete. And when you guys do see pre-stressed concrete, a lot of it is usually in bridges. It's usually done in the lab. It's never done on site like we're seeing in this picture here. It's usually done in a lab under controlled conditions. And then we bring it to site already pre-stressed. And the reason why we have this pre-stressed concrete, because as you guys know from the last quiz, concrete is absolutely shit in tension. It's complete garbage. And what happens is when we start pulling these cords, it compresses that concrete and it keeps the concrete in compression, which is what we want. So that's a little bit off topic. Let's go back to the question. The question says, the shown pictures show the application of pre-tension cables and strings. In concrete beams and slabs, these cables are used to provide an uplift force that counteracts the vertical load applied on structures. Again, it also helps keeping that concrete in compression, which is what we want. And it says, in musical instruments, the strings are pre-tensioned to a specific force, providing a specific musical tone. As if you guys play guitar, you guys will know exactly what this is talking about. I am terrible at music. I'm not entirely sure, but I know, of course, if you put more tension on the string, it's going to have a different response, blah, blah, blah. But here's the key to the question. It says, over time, the tension in these structures are lost and need to be retensioned. And this is an example of what? So here's kind of the first thing. The first thing, it says very specifically over time. And we know that a viscous response is something that is time dependent. So we know right away, because this is over a time period, this is definitely going to be a viscous response, part B. Now, the second thing to notice is it says that the tension is lost. So therefore, the strains become less, the tension goes away, and this is an example of stress relaxation. The tension starts going away, things start to relax. So we know that this answer will be both a viscous response as well as stress relaxation. So we know that the answer is going to be E, which is both B and D. So I'm going to click E and I'm going to check it. We're good to go. We got it right. I just want to make a note that the other response, creep, right here, this is very important. And that's what we see in this picture right here. So creep is actually something that's one of the concrete engineer's worst nightmares, because it's very well understood, but it's also at the same time hard to calculate, because a lot of creep has to do with how you mix the concrete and what are the curing conditions. So let's say I'm mixing a bridge deck and somehow it rains. Well, that's going to change the fluidity of the concrete, and then the creep's going to change. So creep is something that's hard to really calculate on its own. And as you guys will see in the picture above, what happens to creep? Well, it means that under the same amount of load, so let's say I load a bridge, and the load stays the same, nothing changes. What you'll see is it'll start deflecting over time. The bridge will start deflecting even though there's no increase in load, and that's an example of creep. So if we look at a picture here of this, what looks like a deck, we can see that the load's not changing, but Over time, this deck is going to start to sag. So we know that this is going to be an example of creep, which is C. But again, we also have to realize that creep is something that happens over time. So therefore, it is exactly a time-dependent response. So we know it's also a viscous response because it's time-dependent. So we know that the answer is going to be both a viscous response B as well as creep C. And if we look down to, I guess, answer E, both B and C, that's exactly what we want. So I'm going to click E. I'm going to check it. And what do you know? We're 5 for 5. So one question left. We're rolling through this pretty good. Last one. And I'm not going to lie, this is the only one I'm unfamiliar with. As a structural engineer, the other ones I see all the time. Biomechanics, you guys probably know a lot more about this than me. I am terrible at bio. I didn't even take it in high school. I dropped out after science 10. So I'm the worst person to talk to about bio. But let's talk about what the question says and try and get some insight based on that. So it says soft tissue, such as ligaments, muscle, and cartilage, are composed of two phases. And even when it says ligaments, like I don't even know what those are. And it says a solid matrix and a fluid that is mostly water. So all that stuff is bio. I don't really have any idea what it means, but here's what I do know. So it says upon loading, soft tissue exhibits a stiff response, and as the fluid moves out, the stiffness decreases. Now, if we look at a load displacement curve, what happens if the stiffness is decreasing? It means that the response is nonlinear. The slope of a load displacement curve is the stiffness. So I'm going to say that again because it's a nice little fact to know. The slope of the curve is the stiffness. So if we have a linear response, the slope doesn't change. Therefore, the stiffness always stays the same. However, if it's saying that the stiffness decreases, that means that the slope of the load displacement curve is changing. Therefore, we know that this is going to be a nonlinear response. And the second thing that we can also tell from this is it says upon loading, it starts to lose fluid. So it doesn't happen instantaneously. The fluid starts going away over time. So this is also a time-dependent response, which is a viscous response. So for this one, we know that the answer is going to be both A and B. So I'm going to come down here, click both A and B. If we look at part C really quick, or I guess answer C, orthotropic response. Again, orthotropic response has to do with loading direction. It doesn't mention anything about loading direction, so we can kind of discard C right away. We know it's going to be A and B. So if I check that, oh, what do you know? We're good to go, 6 for 6. And that's the quiz, guys. A nice, short, simple video, which is something I think that we've all been needing. The last ones have been quite a lot. I want to thank you guys all so much for kind of getting through those longer videos. I know I could have made them shorter, but I figure might as well have all the information. So in the odd chance you guys do get stuck, it's there if you guys need it, and if you guys don't get stuck, well, of course, you don't need to watch it. So that's why I did it. I hope the video's been helping. That's the whole goal of these, to make your guys' lives a little bit easier. So thank you guys so much for watching. I really appreciate it. I will see you guys in the next quiz, quiz number 22.